sign of the derivative. Tell me when is this function increasing and when it is decreasing.
When it's -10, it's increasing. When it's 0.5, it's increasing.
Right. In other words, from 3/4 to infinity, to infinity, the function is decreasing. And the function is increasing is everywhere else. However, because there is a value here, I have to write it as -infinity 0 union 0 3/4. At a particular value, the function is not increasing, is neither increasing nor decreasing. So the function is increasing on -infinity 0 union 0 to 3/4, and the function is decreasing on the interval 3/4 to infinity. Good. That's all I needed. However, we can choose another function. And then I would like to look at a problem like this. You will see in a moment why. So let's choose a problem from here, and then we'll look at another function, and then move on. Okay, I'll choose 15. It sounds involving. G of x is a positive derivative over, so G prime is positive between -infinity and -3, union 0, 3. Okay, fine. A negative derivative, so G prime of x is less than 0 on -3 to 0, union 3 to infinity. And the derivative equal to 0, so G prime of -3, G prime of -3 is 0, and G prime of 3 is also 0, and G prime of 0 is non-existent. Let's see what the problem is asking us. Draw a graph to match the description given. Of course, there is infinitely many different correct answers. Okay. So what I like to tell my students about problems like these, I consider them gibberish. But it's all this. I have no idea. And look how everything will become super easy. Right now, I don't even want to see what that is. It's awful. But I'm going to do this. Please try to get used to this table because it is crucial for what follows next. Okay, so now, -infinity to -3, 0, 3, infinity. So the first derivative is positive between -infinity and 3, and it's also positive between 0 and 3. I'm done with that. The first derivative is negative between -3 and 0, and 3 to infinity. Done with that. Next, it says G prime of -3 is 0. Done. G prime of 3 is 0. Done. But now it says that G prime of 0 is undefined. It does not exist. I cannot put a number in there. It's D&E. It does not exist. Awesome. So what does the function do between these two? What symbol or sign should I put in here? What does the function do on the interval -infinity to -3? What does it do?
It increases.
Thank you very much. What does the function do between -3 and 0? And 3 to infinity?
Decreases.
Excellent. Now we have to analyze -3, 0. What does this point represent? I'm sorry, -3 whatever, which we can make up where it is not given to us. What is this point -3 whatever for the function g of x?
The max or the min.
Only one. It cannot be at the same time a max and a min. Perfect. Skip this for a moment. What is this point? 3 comma whatever.
Max.
Yes. Good. Finally, 0 comma whatever, the derivative is undefined. We are not told that the function exists or not, so we can invent whatever we want. But what would you consider this? The derivative is undefined. It changes sign in this way. So 0 comma blah, blah, blah. That's why there are many possible answers. What would that point be? If we assume that the function exists at 0, what type of point? Relative min. Excellent. The symbols tell us exactly what it is. Okay, perfect. So here is my take on it. Can you come up with infinitely many answers, correct answers? Yes, you can. So -3 is here, 0 is here, and 3 is here. So the function increases to a point where x is -3, and the y value depends on me. The function is increasing to the point -3 whatever. At 0 comma whatever you want, I can put 0 here if that's what you want, or you can put whatever, but let's say it's 0, 0, for example, or we can choose any other number. The function is not differentiable, so I have to make it into a cusp or a corner. Then it has to go up to 3 comma whatever you want to put, and then it comes down. Here's my graph. Let's go back through these steps again. Increasing to this point. I don't know, I don't care what the y value is. Here it has a minimum, but because the derivative is undefined, it has to be a cusp or a corner or a vertical tangent. It cannot be differentiable. It's not differentiable. It has a tangent on this side and a tangent on this side. Here it has only one tangent. Then it gets to another relative maximum, which can be lower or higher, it's up to you. But then after it reaches this maximum, it drops to whatever. You can make it go up, it doesn't matter. As long as all the conditions are fulfilled, the rest on the side, you can do whatever you want with it. Why is this problem so important? Because it helps us understand how the table works. Without this table, I can only copy the graph from the graphing calculator, but I'm not understanding the calculus behind it. So without this table, it will be difficult to come up with a graph. Okay, I think, any questions, please? Any questions here? Okay, so let's look at another example with another function, and then move on to 3.2. Would you like to choose? Or you want to choose the logarithmic function? Do you want to choose anything? If not, I will.
Can we do 52?
52. Okay, very good. In 52, we have f of x equals the cube root of x minus 1. Remember, one important thing is the cube root is friendly, meaning no restrictions. The domain for the cube root is everything. Nice and easy. Okay. Also, this should immediately be changed into this. Why? Because this I can differentiate, this is more difficult. So I have to see it in the easy format. I'm asked to find critical numbers. What is the first step here that I need to perform to find critical numbers? I need to
That equal to 0.
Yes.
Or on the top.
Yes, so we have f prime of x equals 0 and f prime of x being undefined. Of course, you understand where f of x exists. If it doesn't exist, that's not a critical number then. Good, so let's differentiate. So this is a function to a power. How do we differentiate a function to a power? Anyone, please? Power rule? Anyone?
I'll multiply it by 1/3.
Yes, put 1/3 in front. X minus 1 to which power? We can write it on the side.
-2/3.
Very good. And the key words now, times
Times the derivative.
the inner function prime. The key words are times the inner function prime. It happens that the inner function prime for this problem is 1. So we don't have to do anything. Now, this ugly situation has to be changed into this. Bring down, it has negative power, so it's the cube root of x minus 1 squared. This is not a friendly function, but it is what it is. So that's my page 5. Good. So then f prime of x, I'm going to write it again here, is 1/3 times the cube root of x minus 1 squared. Let's analyze the first option. F prime of x equals 0. Can that happen? When is a fraction 0? When is a divided by b 0? Only when a divided by b is 0, only when is a fraction 0? Anyone, please?
Numerator is 0.
Exactly. So, thank you so much. A over b is 0 only when the numerator is 0. Can the numerator be 0?
No.
No. Now, the other source, f prime of x, is undefined. So let's take a look. When is this fraction undefined?
When x equals 0.
0 minus 1?
Oh, when x equals positive 1.
Exactly. So this is the only critical number for this function. It does not have a critical number coming from f prime being 0, but it has a critical number coming from f prime being undefined. Awesome. Now, yes, we need our table. And yes, we need f prime of x. And then f of x. As I mentioned from the beginning, very friendly function. No problem. And here's 1. And the critical number is from f prime being undefined, which means I cannot put a number in there. It's undefined. There is no number. All I need to do is study the sign. And it's done. So I'm going to say -2. As you notice, I don't put them in the table. This is just for studying the sign. Let's say -2 and 2. -2 minus 1, -3. -3 squared is? -3 squared is?
9.
9. What is the sign of this? 3, the cube root of 9. I only need the sign. I don't care for the number.
Positive.
That's it. Now let's plug in 2. 2 minus 1 is 1. 1 squared is 1. I only need the sign of this.
Positive.
Thank you very much. So x equals 1 is a critical number. What type of critical number is it? Max, min, or none of the above?
None of the above.
None. There is no sign change. So in this case, the critical number did not turn into a max or a min, like this one. This critical number did not turn into a max min because the derivative did not change sign. That's it. We can plug it in so we can determine that value, the y value of 1. So it was is 0. F of 1 is 0. But since the derivative does not change sign, the function is always increasing on its domain. Okay, awesome. Great job. Thank you. So we're moving on to another section, to the next section, which is 3.2. As you notice, we only talked about the first derivative. We will talk about one more, just one more, second derivative. What does the second derivative give? So I forgot to mention, I promised to mention, so before we go to the second derivative, I have to write this. First derivative test. The first derivative test, in short, is what we just discussed. That's the first derivative test. That's it. We used it. I didn't tell you what it was, but now I did. So now we're going to talk about the second derivative and what the second derivative gives about the function. What tells us what about the function. So I'm on page 6. Okay, so the second derivative of a function gives us something called point or points of inflection. And it also gives something called a concavity. So let's discuss them together. If a function does this, or maybe does this, these points are called points of inflection, or in fact inflection point. So this is an IP. What about the concavity? Notice that here the function is opening down, and here the function is opening up. So this is downward, and this is upward. It can be the other way around. It can be opening upward and then opening downward. Downward and upward make the concavity. When I first learned this, my grandma taught me, and I didn't want to. It was difficult for me to understand at that time what concavity meant. And she said, "Does it hold water? Okay, it's opening upward. Does it not hold water? Okay, it's opening downward." I know it's silly, but that's what she taught me a million years ago. Okay, so concavity means, does the function open upward or does it open downward? So in the intervals, of course, plus intervals of concavity. So here we had at the very beginning intervals of increasing and decreasing. They come from the first derivative. The second derivative gives or teaches us or tells us about the function, whether the function opens upward or opens downward. And in short, that is called concavity. Concavity meaning when is the function opening downward? Okay, between this and this, x values, and opening upward. Good. I would like to go and look at concavity and finding point of inflection. Which page is that? 291. So I'm sharing my screen and going to 291. So this time we learn about concavity